In this video, we'll learn about organohalides and how to name them and prepare them. When we first look at organohalides, those are organic compounds that contain at least one or more halogen atoms. So they're found in abundance in nature. And in the organic labs, we usually use them as solvents, as an inhaled anesthetic, and to fumigate. And another term, alkyl-halides. And alkyl-halides are organic compounds that contain at least one halogen atom, and it's bonded to an sp3 hybridized carbon. So organohalide is a more broad term. Alkyl halide refers to the sp3 hybridized ones. When we first examine naming our alkyl halides, remember they're alkanes that contain a hydrogen as one substituent. And so the term is haloalkanes. The halogen is considered a substituent of the parent chain. So a couple steps when we're naming them. Step one, we got to find the longest chain and name the parent, just like we have for alkanes and alkenes and alkynes. The longest chain should contain the double or triple bond if it's present. In the second step, the carbons of the parent chain are numbered beginning at the end closer to the first substituent. And then if the parent chain can be properly numbered from either end, so if we have a substituent one carbon in on both sides, then the numbering begins at the end closer to the substituent that has an alphabetical precedence. So we'll start the numbering on the substituent that has a letter that comes first in the alphabet. Now let's practice. So if we have this compound and we want to name it, when we're looking at it, we figure out the parent chain. There's one, two, three, four, five, six, 7 carbons in the parent chain. And this methyl group is closest to the end. The bromine here, it's a little further in, so it doesn't count as the first side. So we'd number it 1, 2, 3, 4, 5, 6, 7. And we have a methyl group on carbon 2 and carbon 4. Then we also have our bromine on carbon 5. So this compound will be named 5-bromo 2,4-dimethyl heptane. Not too bad, right? Pretty straightforward on our naming. And then let's say we have this compound here. So at this compound, we have our methyl group on carbon 2, or the bromine could be on carbon 2, depending which side we start the chain on. So in this case, we're going to follow step 3, where the substituent that has an alphabetical precedence gets the lower number. So we have our choice between bromine or methyl. Bromine starts with B, so we start numbering on that side. 2, 3, 4, 5, 6. So then this compound will become 2-bromo 5-methyl hexane. So remember, if the substituents can both be the number 2 or the number 3, depending on wherever it is, always go with the one that comes first alphabetically. And then also something that happens with our alkyl halides and their naming is there is that systematic convention that we're using, but sometimes they're also identified first by the alkyl group and then the halogen. So that's why many of the names are alkyl halides. So if we have CH3I, that's proper IUPAC name would be iodomethane, but it's also commonly called methyl iodide. Same thing if we have CH2, Cl2. That one is sometimes called dichloromethane, or occasionally it's called methylene chloride, because the methylene group is a carbon that contains 2 hydrogens. So that's something to be aware of when you're looking at your alkohalides. Is sometimes we use that UPAC name, but sometimes they have a common name convention too. One more example is if there's 3 halogens on it, then that becomes our halo form. And so what we mean by that naming is, in this case, I have chlorines. So this becomes chloroform. If I had 3 bromines, then it becomes, you guessed it, bromoform. So if you have 3 halogens, so if it has the formula of CHX3, then it becomes chloroform, bromoform, iodoform, fluoroform, one of those. So now that we've learned how to name our alkohalides, let's start looking at how to prepare them. First, we're going to briefly touch on radical halogenation first. This is something we've seen already, so we're not going to spend too much time on it. But if you remember, radical halogenation is where we can start with alkanes, use Cl2 or Br2 to create an alkohalide. So if you remember the mechanism for a radical halogenation, we have the initiation step, where we first form the radical, then our propagation step, where we take off a hydrogen and add the halogen in its place, and then our termination steps. And so the overall mechanism is your methane plus chlorine gives you chloromethane and HCl. These are steps, and the mechanism for this we've seen already. And with our radical halogenation, we can do more than one halogenation. So what that means is during a radical halogenation, we may not just end up with that methyl chloride. Instead, the methyl chloride can go through another radical halogenation and become dichloromethane, or it can go through another one and become chloroform, or it can go through a 4th radical step and become carbon tetrachloride. So radical halogenations, you can have multiple halogenation events. It doesn't just do it once, but each one of these steps and arrows goes through the exact same mechanism that we learned before for radical halogenation. And to complicate things even further is if there's different kinds of hydrogens on our molecule. So for example, on 2-methylpropane, I have a hydrogen here that's on a tertiary carbon and a hydrogen that's on a primary carbon. So we have tertiary versus primary. That can actually give different products and lead to a ratio of products. We see during the course of this reaction that a tertiary, we get about 35% of the tertiary substitution and about 65% of the primary substitution. And then we can also get the dichlorination, trichlorination, or tetrachlorination. So we can also get multiple chlorination events still. And we can actually calculate a reactivity order towards the different chlorinations and figure out which hydrogens are more likely to get removed and replaced with a halogen. So looking at how this replacement can happen in the reactivity, we're focusing on primary, secondary, and tertiary carbons. So hydrogens on primary carbons, hydrogens on secondary carbons, and hydrogens on tertiary carbons. And based on quantitative analysis of a reaction, we can figure out the relative reaction rates for each type of hydrogen. So if it's a primary hydrogen, the reactivity is 1.0. Secondary hydrogen is 3.5. So that's 3.5 times as likely to be substituted with a halogen versus a primary. Tertiary is 5.0. So that's 5 times more likely it's to be substituted than a primary. So tertiary is a much more favorable one to be substituted. And when we think about this, it kind of makes sense. Looking at our substitution patterns, during the course of the mechanism, the carbon forms a radical. When a carbon forms a radical, that carbon has less than 8 electrons. If it has less than 8 electrons, it's considered electron deficient. That's very similar to our carbocations. So if it's similar to our carbocations, it should follow the same stability trend that the carbocations do. And so we do see that with the radical halogenations. They follow the same stability trend. So a primary radical is not as stable as a secondary radical, which isn't as stable as a tertiary radical. Just like with our carbocations, the primary carbocation is the least stable and the tertiary is the most stable. Same with the radicals. So it follows our carbocation trend or stability. And we know that makes sense because our radicals are carbons that have less than 8 electrons. Carbocations are carbons that have less than 8 electrons. So now let's look at one new type of halogenation called allylic halogenation. So when we have a double bond, that's going to affect the regioselectivity of our halogenation. The primary, secondary, and tertiary are no longer the main factors. So instead, if we look at our bond dissociation energies down here, figure out which one would be the most reactive towards halogenation. Our blue hydrogen here has a bond dissociation energy of 364. It's the lowest of all 3 options. Since it's the lowest of all 3 options, this is our easiest bond to break. Which means that's the bond, that's the hydrogen that's most likely to be abstracted for a radical halogenation. You can see the hydrogen on our double bond here. That's our hardest hydrogen to remove. And that's because its bond dissociation is the highest. So let's now examine why this blue one is the easiest to remove. We're going to look a little bit at the mechanism to figure out why that hydrogen is easiest to remove. So if we have our double bond here, and I have my bromine radical. So I've already done that initiation step. We're working on the propagation part. Make a little note to ourselves. Already initiated. So that bromine radical is going to come and grab a hydrogen and move electrons to the carbon. Now I have a radical that's next to my double bond, or have a radical that's in the allylic position to my double bond. So what can happen is the double bond can actually shift through resonance, which means now the radical is over on my top carbon here. So since the radical is resonance stabilized, that's why that hydrogen is so much easier to abstract. So we can say it's resonance stabilized. That plays a bigger factor than primary, secondary, tertiary. Resonance stabilized will be your more stable radical, because that hydrogen deficiency is spread over multiple carbons, not just on one carbon. So then if we have our second bromine radical here, they can come together to give us our product. And so this one at the end here, that would be our termination step. And then besides using Br2 and light, in order to avoid competing halogenations, we can use a compound called NBS, N-bromosuccinimide. And so what NBS does is it has a ring here, and the nitrogen is bonded to the halogen. Light will then cause the bond to break, which will then have the halogen removed as a radical. The nitrogen is also a radical, but it's stabilized across all of these atoms. So this becomes stabilized by resonance. And then our bromine radical here can then go and do a single halogenation. So we can use NBS to avoid multiple halogenations. So let's practice this and see if we can predict the products from our halogenation. So if we start with this halogen and I use NBS and light, this way I avoid multiple halogenations. What sort of products will I get? Well, the first step, NBS, is kind of the equivalent of our bromine radical. So the bromine radical will come and take one of the allylic hydrogens. And since we only have one allylic hydrogen, it's going to remove that one. So it goes through a radical mechanism to abstract the hydrogen. This gives us our radical there. The radical is then stabilized through resonance to give our intermediate here. So a radical is stabilized through resonance. So then in a side reaction, our NBS is then going to go and react with the HBr we just formed to give us NH and Br2. That Br2 is then going to go and react with our allylic radical. So let's say the radical's in this position. Oops. It'll go and react to give us a bromine here plus a bromine radical that can then go and restart the reaction. Or if our allylic radical is in this position, when that one reacts with Br2, it then goes and gives us a product where the bromines in this position. So these two compounds are the two possible products we can get from the allylic radical halogenation of this compound with NBS. So now let's look at a new way of preparing our halogens. One other way to prepare an alkyl halide is to prepare it from an alcohol. So with our alkyl halides, if I treat it with HCl, HBr, or HI, I can get an alkyl halide. And the rate of the reaction in primary and secondary alcohols is much slower than in a tertiary. So if we look at kind of the rate of reactivity, methyl alcohols, they're the slowest, so methanol is the slowest. Primary alcohols, still pretty slow. Secondary, and then tertiary. Tertiary are ones that react okay with it. Now, one thing to notice is HF isn't listed here. HF takes a different set of circumstances. So with all these other ones, if I add the alcohol to the appropriate hydrohalogen acid, I'll get the corresponding alkyl halide. It doesn't work with HF. So with HF, if I have my alcohol, I'll need to react with HF in pyridine. Pyridine's a type of base. So pyridine is a 6-membered ring with the nitrogen in it. It's aromatic. And what that'll do is that'll convert that alcohol to a fluorine. The main downside with forming an alkyl halide this way is there's a lot of side reactions that can occur. And it doesn't really work with methyl or primary. They just don't really react. Secondary does a little bit, but it takes a lot of heat. So really this way only works well for tertiary. So if you have a primary alcohol and you want to convert it to an alkyl halide, you couldn't use this method. Instead, there's a couple other reagents we can use to get an alkyl chloride or an alkyl bromide. So let's say we have our primary alcohol, and I want to turn it to my alkyl chloride. The reagent I can use is SOCl2, and that is also in pyridine that will shorten as PY. So now if we look at the mechanism for it so we can kind of understand how this is happening, what's going to happen is I have my OH and SOCl2, thionyl chloride, and SOCl2 looks like this. So this is thionyl chloride. What happens in the first step of the mechanism is the lone pair from the oxygen comes and attacks the sulfur. That moves electrons up to the other oxygen. So when that happens, the negative charge on the oxygen will then move back down to create a double bond, and it kicks out one of the chlorines. That chlorine that got kicked out comes back and attacks the carbon that positively charged oxygen is attached to, which then moves electrons to the oxygen. So this whole thing leaves. This whole part of the molecule here leaves. we'll call it our leaving group. So this whole part leaves the molecule. When that happens, we have our chlorine. And so the electrons move to the double bond there and kick out the chlorine. So we end up with the side products, in case you're wondering, of SO2 and HCl. We don't really care about those side products. All we care about is our alkyl chloride that we made. Not too bad. And so this way works on our primary ones, on our secondary ones. It's useful to get that substituted halogenation. So now let's look at how we can get our alkyl bromide. Again, if we start with our alcohol, this time we're going to react it with the compound PBr3, phosphorus tribromide. And that gets done in ether as a solvent. So what that'll do, since you see a bunch of bromines here, it's going to substitute the alcohol for a bromine. And so looking at the mechanism for how this occurs. If we start with our alcohol, it's going to react with our phosphorus. And so the lone pair from the oxygen will attack the phosphorus. That then kicks out a bromine. That bromide ion that got kicked out then goes and attacks the carbon where that positively charged oxygen is attached to. The electrons then move to make a double bond between the phosphorus and the oxygen. And then this again would be our leaving group, which gives us our alkyl bromide. And P, Br, Br, O, H. A couple things about the mechanism here. If there's a stereocenter, then an inversion will happen. So what that means is if it's S, if the starting stereocenter is S, the new stereocenter will be R. This also happens with the SOCl2. So with SlCO2 and PBr3, you're going to get an inversion of the stereocenter. So if it starts S, it's going to become R. If it starts R, it's going to become S. And this works really well for primary and secondary alcohols. Doesn't work as well for tertiary ones because tertiary ones are really bulky around that carbon. So it's really hard for that bromine to come in and attack it. So if you have a primary or secondary, or methyl, SOCl2 and PBr3, those are the two you want to use. So these are the two reagents we want to use if we have primary or secondary or methyl. If you have a tertiary, then you want to go with the HCl or HBr route. And so now we know a little bit about how to prepare alkyl halides. We can either do radical halogenation. We've also seen radical allylic halogenation. We can convert alcohols into alkyl halides using either the hydro acid or, if it's a primary or secondary, SOCl2 or PBr3. Next, we're going to start looking at reactions that alkyl halides can do.